Morning everyone, thank you for joining us for this GCSE Chemistry live group tutorial. I hope everyone had a nice evening. Today's topic is atom economy and concentration reactions, and as usual this session on chemistry will be run by our brilliant chemistry tutor Aman, who lots of you know already. Aman studies medicine at King's College London and has done over 150 lessons with my tutor. So this will be a 1 hour session as usual and will end at 11:15. And this session will be recorded, so you'll be able to access it from the My Tutor YouTube channel as of this afternoon, as well as lots of other shorter chemistry related sort of topic videos that are there, which should be really handy for you guys if you're looking for some more revision tools and to help consolidate your knowledge on the topics that Aman has gone over in these tutorials. So I'm Tilly, I work at My Tutor, and Aman is our tutor today, as I said. If you have any questions for either of us during the session, just drop them in the chat or the Q&A box, and we'll keep an eye on that throughout, and then have a little session of Q&As at the end for anything that we might have missed. I'll just wait a few more moments as people are joining. Let's have a look. Brilliant. Cool, okay, Aman, if you're all ready, then let's get started.
Hi everyone, just a reminder to have a calculator because we're still doing the quantitative side of chemistry, so we'll still be doing lots of calculations today, and it will run pretty much the same as I did on Wednesday and Monday. So if we start off with a recap of what we covered on Wednesday. So the first question on the screen is about constructing a balanced equation from the moles and masses that we've got on the screen. Before we tackle this question, I just want to say that normally you wouldn't be given the formulae of each of the compounds there. So you can see we've got barium chloride, aluminium sulfide, and barium sulfate. Usually you wouldn't be given those. I've given them here just for simplicity. But what I will do is go through now how you would calculate those compounds. So you'll remember last week we looked at ionic compounds and ionic bonding. So remember, when we're forming compounds, we look at the charges of elements. So barium is in group 2, and that means it has a 2+ charge. So it forms a Ba2+ ion. Chlorine is in group 7 and therefore forms a Cl- charge, and that's because it has 7 electrons in its outer shell, so wants to gain 1 electron. So that means if it gains that 1 electron, it forms a chloride ion with 1 charge. When these two then react, remember, if barium has 2 electrons to give, but chlorine only wants 1, that means for barium to have its full outer shell, it must give its 2 electrons to 2 chlorine ions. So it forms BaCl2, and that's why it's BaCl2. Aluminium sulfate's a little bit trickier because we've got the sulfate ion. Now, I've had a look at the curriculum for all of the exam boards, and it looks like the hydroxide ion, which is OH-, and the sulfate ion, which is SO4 2-, are ions that they expect you to know in the higher tier. So that means you need to know the charges on these ions, and that's what's going to help you to be able to come up with the chemical compound formula for things like aluminium sulfate. So we know aluminium is in group 3, so it forms an Al3+ ion, and sulfate is SO4 2-. Yeah, I'll change the color of my pen. So sulfate is SO4 2-. So that means when they react together, aluminium has 3 electrons to give, and sulfate can only accept 2. So if sulfate accepts 2 electrons and aluminium has 3 to give, that means that there's going to be 6 changes that's going on. And so aluminium, there will be 2 of them to have 6 electrons, and sulfate, there will be 3 of them to accept those 6 electrons. So it'll be Al2, SO4, 3, like that. And then barium sulfate is exactly the same because barium's a 2+ ion and sulfate is a 2- ion. When they react, you get BaSO4, so there's just 1 of each. Okay, so let's tackle the question then. We need to form a balanced equation for the reaction. So does anyone remember from Wednesday how we do that? Okay. Hello, sorry, so I asked, does anyone know from Wednesday how we construct a balanced equation for this reaction? So we've got barium chloride reacting with aluminium sulfate, forming barium sulfate and aluminium chloride. We need to form a balanced equation. How do we do that? Yep, you work out the moles. Excellent, well done everyone. So to work out the moles then, remember our reaction, or the equation for that, is that the number of moles equals the mass over the MR. So in this question, we need to calculate the number of moles for all of the reactants and all of the products. So for barium chloride, that would be 1,248 divided by the MR of barium chloride. So how do we calculate the MR of barium chloride? What do we need to do to calculate the MR? Or what is the MR of barium chloride? So we've been given the ARs, so Ba is 137, chlorine is 35.5. So what's the MR of barium chloride? Okay, great. So people are saying 137 plus 71, which is equal to 208. Excellent, well done. So it's 208. So to calculate the number of moles of barium chloride, it's 1,248, which is the mass in grams, divided by 208. So what is 1,248 divided by 208 then? Should get a nice answer there. Great, excellent. So it is 6, well done. So that means the number of moles of barium chloride is 6. What about the number of moles of aluminium sulfate? So we've got a mass of 684. What's the MR of aluminium sulfate then? So Al is 27, there's 2 of them, so it's 27 times 2. We're then adding in sulfur, which is 32. And remember there's 3 sulfurs, 3 oxygens, and 12 oxygens and 3 sulfurs in aluminium sulfate. So what do we think? What's the MR of aluminium sulfate? Someone's asking me, isn't the MR of barium chloride 172.5, not 208? Remember, barium chloride is 1 barium plus 2 chlorines, and 2 chlorines make 71, so it's 35.5 times 2. So barium chloride is BaCl2. So it'd be 137 plus 71, which is 208. Okay, so the MR of aluminium sulfate. So someone's saying 342. Does everyone agree with that? Is the MR of aluminium sulfate 342? Yep, okay, great. So if it's 342 then, what is the number of moles then? So the mass of aluminium sulfate is 684. We divide by the number of moles. So 684 divided by 342, that's nice and easy. That's going to give us 2. So there are 6 moles of barium chloride, 2 moles of aluminium sulfate. Then we have barium sulfate and aluminium chloride. So what is the MR of barium sulfate? So you should find that the MR of barium sulfate is 233. So the number of moles of barium sulfate will be the mass divided by the 233. But you'll see we don't have a mass. So do you remember what we do to calculate the mass of barium sulfate? So remember, in these questions, what do we do to calculate the mass? So in reactions, the total amount of reactants will be equal to the total amount of products. So if we have a look, our barium chloride and our aluminium sulfate give us a total mass. Someone's asking what's the unit for mass. The unit for mass is grams. Good, excellent. So the person that's saying reactants equals products, brilliant. So what's the mass of barium sulfate then? So we've got 1248 barium chloride and we've got 684 aluminium sulfate. That gives us a total mass of 1,932. So we then subtract the 534 aluminium chlorides, leaving us with 1,398. Excellent, well done. So there's 1,398 barium sulfates. Good. And then we divide by the MR of barium sulfate, which would be 137 plus 32 plus 64. So that gives us an answer of 6. So the number of moles of barium sulfate is 6. And then the final one we need to do is aluminium sulfate, or sorry, aluminium chloride. So at the moment, we've got 6 barium chlorides, 2 aluminium sulfates, 6 barium sulfates, and then we've got aluminium chloride, which is AlCl3. So Al is just 27. We add that to 35.5 times 3, which gives us an MR of 133.5. And then the mass is 534. So if we do 534 divided by 133.5, we get 4. So now we have the moles of each of them. We can write our balanced equation. So our balanced equation will be 6BaCl2 plus 2Al2SO43, which then goes to 6BaSO4 plus 2AlCl3. Now, what you can hopefully see is that they're all even numbers. And when we write balanced equations, we want it to be the simplest equation possible. So actually, we can divide all of these by 2. So it will be 3BaCl2, 1Al2SO4, 3BaSO4, and 1AlCl3. So hopefully that makes sense. Okay, let's go on to the next question then. If 2 grams of hydrogen fluoride are exposed to 4.5 grams of silicon dioxide, which substance is the limiting reactant? So does anyone remember how we calculate the limiting reactant? What do we need to do to calculate the limiting reactant? So we covered this on Wednesday. So to calculate the limiting reactant, we need to calculate the moles of both of the reactants and see if one is limited. Good, excellent. So if hydrogen fluoride has 2 grams, the number of moles of hydrogen fluoride will be the mass divided by the MR. So hydrogen fluoride has an MR of 1 plus 19. So remember, that's 1 plus 19. But if we have a look, the question says it's unbalanced. So we need to balance our equation first. So how do we balance this equation then? So if we have a look, what isn't balanced, we've got 1 hydrogen here, but 2 on the product side, 1 fluorine, but 4 on the product side, 1 silicon, 2 oxygens, 1 oxygen. So what do we need to do to balance that equation? What's going to help us balance it? So if we have a look, we can first of all notice that we need 4 fluorines, but we've only got 1. So if we put a 4 here, that's going to make our fluorines 4. But then it changes our hydrogens to 4. So we need to make sure our product side hydrogens are also 4. So if we put a 2 here, our hydrogens become 4. Then let's look at the oxygens. The oxygens are 2 on the product side and 2 on the reactant side. So that is a fully balanced equation. Well done. So now let's have a go at calculating the moles of hydrogen fluoride. So that will be 2 divided by the MR. So the MR was 20. So 2 divided by 20 is the number of moles of hydrogen chloride, which gives us an answer of 0.1. So we've got 0.1 moles of hydrogen fluoride. And then if we use our reaction, we can see that 4 moles of hydrogen fluoride reacts with 1 mole of silicon dioxide. So the ratio is 4 to 1. But we've got 0.1 moles. So that means when hydrogen fluoride is reacting with silicon dioxide, it's actually a quarter of that. So we divide by 4. So that means the number of moles of silicon dioxide that are reacting are 0.025. And then we can calculate the mass of silicon dioxide. So the mass of silicon dioxide will be 0.025 times the MR. So the MR will be 28 plus 32, so SiO2, so 28 plus 32. So we times by 28 plus 32. which is then equal to 1.5. So then that means we have 1.5 grams of silicon dioxide. And if we have a look at our question, we can actually see we started off with 2 grams of hydrogen fluoride, but we have 4.5 grams of silicon dioxide. So what's in excess is the silicon dioxide, and therefore the limiting reactant is the hydrogen fluoride. Well done to everyone that sent me answers. Yep, HF is the limiting reactant. Okay, we'll finally do this percentage yield question and then move on to today's question. So does anyone remember the equation for percentage yield? What's the equation for percentage yield? Someone's asking, if we balance equations, which elements are better to balance first? That's a really good question. So it doesn't really matter. Just start off wherever you see a difference between the reactants and the products, balance one and then go from there. That's what I always do. You can't really go wrong by balancing one and then seeing. Sometimes you might have balanced that one incorrectly based on the other reactants and products, but it's just a bit about trial and error. Good. Actual mass divided by the predicted or theoretical mass is the equation for percentage yield. So yeah, it's the mass produced. So that's the mass that you produce in, for example, a classroom, divided by the total mass or total theoretical mass. So remember, whenever we do these questions, we calculate a total theoretical mass and then we multiply it by 100. Okay, great. So the actual mass divided by the total mass. Well done. All right, so if we calculate the percentage yield then of titanium in the following reaction, where 260 grams of titanium chloride produces 48.5 grams of titanium. First of all, let's check it's balanced. So if we have a look, we've got 1 titanium, 4 chlorines, but only 1 chlorine. So if we want to balance those, let's put a 4 here. That now means we have 4 chlorines, but we also have 4 sodiums. So let's check our reactant side. We need a 4 here to make it 4 sodiums. So in actuality, if you hadn't balanced that question, it wouldn't have made a difference because in this question, we're just looking at titanium, so it doesn't matter. So let's have a look then. So we've got titanium in the following reaction where 260 grams of titanium chloride reacts to produce. So the equation is mass produced over total theoretical mass. So titanium chloride plus sodium. So 260 grams of titanium chloride produces 48.5 grams of titanium. So let's calculate the number of moles of titanium chloride. Remember, that is the mass, 260, divided by the MR. So the MR of titanium chloride will be 48 plus 35.5 times 2, which will give us an answer of 190. So then we do 260 divided by 190. 260 divided by 190 gives us a number of moles of about 1.369. Then we do 1.369 and we multiply by the MR of titanium. Great, excellent. Person that's saying 1.36, great, well done. So 1.369, we multiply by the MR of titanium. Titanium has an MR of 48 or an AR of 48, which gives us a total mass of 65.68 or 65.7 to 3 significant figures. So that's our total theoretical mass. The mass produced was 48.5. So if we do 48.5 divided by 65.7, we then multiply by 100. Remember, this is a percentage yield question, so we need a percentage. Great, so people are saying 73.8%. That's exactly correct. Well done. Okay, so does anyone have any questions about those three before we move on to today's content? Good, everyone that's saying 73.8, you're exactly correct. Okay, brilliant, let's move on then. So today we're looking at atom economy or atom utilization, which is a measure of the percentage of the atoms in the starting material which end up in the desired material. The remaining percentage of atoms end up in other products. So what that means is if, for example, we have AB plus CD reacting together, and then that produces AC plus BD, let's say, then the atom economy would be, for example, if AC is our desired product, it would be AC divided by the reactants, which would be AB plus CD. So that would be the atom economy here. So it's the percentage in the required product divided by the reactants. So we use the MR to help us with that. And the waste products can sometimes be harmful. in which case they will have to be made harmless. So something like sulfur dioxide is harmful to the environment. It produces acid rain. So we tend to remove that from the atmosphere. So I'm sorry, I don't know why that slide has messed up, but the atom economy percentage is just the MR of the product that you want divided by the MR of the reactants. So the sum of the MR of the reactants. So the Haber process was on the screen. And if you remember, the Haber process is about making ammonia, which says that hydrogen plus nitrogen would go to form ammonia, which is 3NH2. And what we can see is that all the reactants produce one product. So the atom economy of this reaction is 100%. And that's because all the reactants produce one product. And we want a high atom economy because that then conserves resources and minimizes pollution. So let's have a go at a question then. Before we go on to those questions, does anyone have any kind of questions about atom economy or how we calculate atom economy? Any questions about that? Can I just check, is my sound transmitting okay, or am I cutting out?
It's absolutely fine for me. Okay. It seems to be all clear.
That's fine. Okay, just because we've got some messages coming through. That's absolutely fine. All right, so atom economy questions then. Someone's just asked me to explain the Haber process again. Yeah, that's absolutely fine. So the Haber process is about nitrogen reacting with hydrogen and producing ammonia. So remember, nitrogen plus hydrogen goes to ammonia. And I haven't balanced that there, but if you did want to balance it, it would just be like that. Oh, sorry, that's a 2. So what happens there is that we can see that all the reactants form one product. So the atom economy there would be 100%, because remember, the atom economy is the MR of the product. So the MR of this product divided by the MR of the reactants. So if we only form one product, there's no wasted reactants. Okay, great. So someone's asking me, is atom economy about moles? No, it's only about the MR. Okay, brilliant. So let's go on to this question then. So we've got 2 reactions here, and we need to calculate the percentage economy for both reactions in order to determine which reaction has a better economy. So they've not told us which product we want, but we can always assume that we want the product that's not water, because usually when we do reactions, it's not water that we want the other product. So in this case, it's copper chloride. So the MR of copper chloride will be 63.5 plus 71, which is 35.5 times 2. So if we do 63.5 plus 71, we get an answer of 134.5. So the MR of copper chloride is 134.5. We then divide by the MR of the reactants. So in this case, it would be copper carbonate and 2HCl. And what's really important here is that we do this 2HCl. And that's because, remember, the atoms are neither created nor destroyed. So when we're calculating the atom economy, we need to know how much of each there is. We don't ignore the numbers in front. All the other reactions, we have really ignored those when we're calculating the MR. But in this question, or in atom economy questions, we always look at the numbers in front. Good, so let's, the HCl then will be 2 plus 71, and that's because it's 2 times 1 plus 2 times 35, which gives us 73. And then we add that to the MR of copper carbonate, which will be 63.5 plus 12 plus 16 plus 16 plus 16, which gives us an answer of 123.5. And then if you put that into your calculator, remember we multiply by 100 because, again, we want a percentage. So we get 134.5 on the top, then it's 73 plus 123.5. We then times by 100, and you should get an answer of 68.4% to 3 significant figures. Great, so 68.4%. Okay, well done to everyone that gave me answers. Just make sure you're putting in the correct numbers and you've calculated the MR correctly. Where you might have gone wrong is if you haven't included the 2. Someone's asking me, what does the L mean? That means a liquid. So remember, water usually is a liquid. HCl is aqueous because it's an acid, hydrochloric acid. Copper chloride forms an aqueous solution, and copper carbonate is a solid. That's what these are, the state symbols. Okay, let's look at the second reaction. Again, we're forming copper chloride, so it's going to have an MR of 134.5. So let's just remember this first reaction had an atom economy of 68.4% to 3 significant figures. Now, if we look at the second reaction, it's copper chloride, which is 134.5, divided by 2 HCl, which again will be your 71 plus 2, which is 73, plus CuO, so that forms, so copper oxide, so 63.5 plus 16. So 63.5 plus 16 will give you an answer then of 79.5 over here. So we multiplied by 100. So if we do that into the calculator, what's our atom economy for the second reaction? Someone's asking what's the difference between aqueous and liquid. So aqueous means that it's dissolved in water. Liquid is the state that it's in. So aqueous solutions can be liquid, but they're not just pure liquids, they're dissolved in water. So we've got answers of 88.2. So is everyone happy with that answer? Is that the correct answer? Is that what everyone else thinks? Yep, 88.2. Okay, great. So yeah, 88.2. So which reaction has the better atom economy then? Which reaction has the better atom economy? Reaction 1 or reaction 2? Good, reaction 2, excellent. So reaction 2 has the better atom economy, and that's because it's 88.2%, whereas the first reaction was 68.4%. Okay, let's do a couple more questions on that then. So the first one here, we've got nickel oxide reacting with carbon to form nickel plus carbon monoxide, and that's monoxide because there's only one oxygen there. Calculate the percentage atom economy for the reaction. So what do we think? What's the atom economy for this reaction then? How are we going to calculate that? And they've told us it's to produce nickel, so we know that the the product that we want is nickel. So that's nice and helpful. So if we have a look at the atomic mass of nickel, it's 59. Check it's balanced. So if we have a look, NiO plus C, NiO plus C, so it's all balanced. So that means the atom economy then will be 59 on the top, which is the AR of the desired product. Then we do it divided by the MR of the reactants. So NiO will be 59 plus 16, which is 75. And then C, which is 12. So 59 divided by 79 plus 12 times 100. So what is the atom economy then of this reaction? Yep, 59 divided by 87 is correct. So what's the atom economy then? Okay, 67.8%. Excellent. All right, let's do the second question. So 67.8%. So the second question, calculate the atom economy of the following equation, assuming that potassium, so this is potassium nitrate, is the desired product. So we've got potassium hydroxide plus nitric acid, so that's nitric acid there, forms potassium nitrate plus water. So we want the potassium nitrate, that's our desired product. So the MR of potassium nitrate will be 39.1 plus 14 plus 16 times 3. Check it's balanced. We've got 1K on the reactant side, 1K on the product side, 1 nitrate, 2 hydrogens, and 1 oxygen, plus 3, which is 4 oxygens on the reactant and product side. So yeah, that's all balanced. Okay, so the MR of potassium nitrate will be 39.1 plus 14 plus 16 times 3, which gives us an answer of 101.1. We then look at the MR of the reactants. So the reactants are potassium hydroxide, which is 39.1 plus 16 plus 1, so 39.1 plus 17, which gives us an answer of 56.1. And then nitric acid will be 14 plus 1 plus 16 times 3. Again, 15 plus 16 times 3, which gives us 63. We then multiply by 100. So what is the atom economy of this one then? What do we think? We've got 101.1 divided by 56.1 plus 63 times 100. Okay, so we've had our first answer come through of 84.9%. Does everyone agree with that? Is it 84.9? Yes, good. Good, 84.9. So remember, 3 significant figures. Brilliant. Okay, so that's our atom economy questions. Before we move on to concentration questions, does anyone have any questions about atom economy? It doesn't tend to get much harder than that. It is always just looking at a question. Usually you might have to balance the equation, and always check if an equation is balanced. It only takes a few seconds to check that, so just make sure it is balanced, and then you can go ahead using the equation of using the MRs. So any questions on that before we move on to concentrations? Okay, let's go on to concentrations. Again, sorry, I don't know what's messed up that slide. So concentration equals the mass of a solute. So in grams, the mass of solute divided by the volume. And before we do any questions, what's really important is that we know the units. So the mass is always in grams and the volume is always in decimeters cubed. Now, if you haven't heard of decimeters, it's essentially the same as litres, but in chemistry questions, they tend to report it in decimeters. Centimeters cubed is equal to millilitres, but decimeters cubed is equal to litres. Why do we calculate a concentration? Well, it tells us the amount of solute that's dissolved in a certain volume. So if we want to know, if we've, for example, dissolved copper carbonate in water, and we want to know how much copper carbonate is in there, then that would be our concentration of copper carbonate. And this third point on the slide was talking about exam questions often give volumes in centimeters cubed. So they almost try and trick you. So it's really important that you convert to decimeters cubed. So how do we convert from centimeters cubed to decimeters cubed? Does anyone know what's the conversion between centimeters cubed to decimeters cubed? Good. So some people are saying times by 1,000, some people are saying divide by 1,000. So the way I always remember it, if centimeters cubed is a milliliter and decimeters cubed is equal to a litre, we know that there are less litres than milliliters because 1,000 milliliters makes 1 litre. So we always divide by 1,000. So for example, if this was 30 centimeters cubed, we would divide by 1,000 to give us 0.03 decimeters cubed. So it's divide by 1,000, not multiply. Good, well done for everyone that gave me the correct answer there, well done. So just try and think about it in the sense of millilitres and litres, and I think that might help. Excellent, okay, so we've got our equation, mass divided by volume, and we know our conversion. So let's tackle some questions. So a student did an experiment using 20 centimeters cubed of sodium hydroxide solution with a concentration of 0.18 moles per decimeter cubed. We've got a relative formula mass there. Calculate the mass of sodium hydroxide in 20 centimeters cubed of the solution. So in this question, they're trying to confuse you. They've given you the relative formula mass, but as I said, with concentration questions, we don't need the relative formula mass. All we need is the concentration equals the mass divided by the volume. So we need to calculate the mass. So if our triangle is concentration, is mass, which I've put in grams, divided by the volume. So if we want the mass, it's concentration times volume. So concentration times volume. We've got a concentration, which is 0.18. Our volume, if we have a look, is in centimeters cubed. So it's really important we convert that to decimeters cubed. So we divide by 1,000, which gives us 0.02. So remember, when we divide by 1,000, we're moving the decimal place 3 points. So if it goes from 20, we move it 3 points. So imagine it's here. It's going to go 1, 2, 3. So it's going to go here, so we add a 0 there. So it becomes 0.02. So 0.18 times 0.02. So if you put that into your calculator, you should get an answer of 0.0036. And remember, it will be in grams. And that is the mass of sodium hydroxide that was dissolved in this solution. Good, excellent. Well done to people giving me the correct answer. Well done. Okay, let's have a go at the second question. So calculate the concentration of 10 grams of magnesium chloride in 1 decimeter cubed of solution. So we've got them in the right units there, 10 grams, 1 decimeter cubed. So the concentration is the mass divided by the volume, so 10 divided by 1. So that gives us a nice concentration of 10 grams per decimeter cubed. Remember to always give the units, so grams per decimeter cubed. The third question then. we've got a concentration that we need to calculate, 2.3 grams, 500 centimeters cubed. So one of the units is off. So centimeters cubed. Well done to people giving me the answer for the previous question. 500 centimeters cubed, we convert to decimeters cubed, again, divide by 1,000. So you're going to end up with 0.5. That's in decimeters cubed. So that means the concentration is 2.3 divided by 0.5. So 2.3 divided by 0.5 gives us an answer, as people have been saying, of 4.6. Yeah, good, well done. Not 4.006, it'll just be 4.6. Excellent, well done to the people answering those questions. Okay, then our final question on concentration, or this calculation for concentration. Calculate the mass required to make 250 centimeters cubed of a 1.5 gram per decimeter cubed solution of sodium chloride. So again, we're rearranging the equation. We need to calculate a mass. So we do concentration times volume. So concentration, we have, is 1.5. Our volume is 250 centimeters cubed. So again, we need to convert to decimeters cubed, which will give us an answer of 0.25. So remember, the decimal place moves 3 places. So imagine it's here, 1, 2, 3, so 0.25. So 1.5 times 0.25 should give you an answer of 3.75. So 3.75 grams is the mass of sodium chloride that is dissolved to make that solution. Excellent, great, well done everyone. So before we move on to the second concentration equation that we need to know, does anyone have any questions about concentration or this equation or any of those questions that we've just answered? Again, well done to everyone that's been giving me answers. So someone gave me an answer of 0.375. It's not 0.375, it is 3.75. And that's because, remember, we convert the 250 centimeters cubed to decimeters cubed. The mass, the concentration is 1.5, so it's 1.5 times 0.25, which gives you an answer of 0.375. Okay, well done everyone. So now someone's asking me the difference between aqueous, liquid, and solute, I believe. So solute is something that's dissolved in a solution. Aqueous is dissolved in water, and a liquid is just a liquid on its own. It's only got liquid particles in there. So water is a liquid, but an aqueous solution would be something like copper carbonate dissolved in water. All right, so hopefully that clears that up for you. Okay, let's go on to the second concentration question. Again, sorry about the slide. So the second concentration question is molarity. Molarity is essentially using moles now instead of the mass. So it's exactly the same question, same equation. So it's the concentration equals the number of moles divided by the volume. So instead of the mass, we use the moles. And the reason this works is because if you remember, moles, do you remember what moles are? Does anyone remember what moles are from Monday's lesson, or what the definition of a mole is? So it's the AR in grams. So essentially, moles is looking at the AR. So we've got the number of moles divided by volume. Good. So in concentration then, moles per decimeter cubed. So that's what the unit is, moles per decimeter cubed. Oops, sorry. Hi Tilly, can you still hear me?
Yep, can you hear me fine?
Okay, so my screen's just completely gone. Okay, that's fine.
Is it all okay?
I think so, hold on, okay. So moles equals, concentration equals the moles divided by the volume. So it's exactly the same equation that we used last time, but instead of mass, we use moles. So to do these questions, again, exactly the same. So let's have a look at this question here. Determine the number of moles of potassium hydroxide present in 125 centimeters cubed of 0.255 m solution. M is a unit for molarity. Molarity is the same as concentration. It is essentially moles per decimeter cubed. That's what M is. So that's a concentration there, and we need to calculate the number of moles. So if we look at our triangle, concentration equals moles. Oops. Moles divided by the volume. So if we want the number of moles, we do the concentration times the volume. So the concentration is 0.255. We times by the volume, which is 125. Remember, we convert that to decimeters cubed, so we divide by 1,000, which gives us an answer of 0.125. So what's the number of moles then of potassium hydroxide? So 0.255 times 0.125. So what's the number of moles of potassium hydroxide? Okay, so we've had our first answer come in of 0.0306. 0.03, good, yep, so remember always to three significant figures. So 0.03. So the only thing I would say is that to three significant figures, it is 0.0306. Remember, people that are giving me 0.03, that's three decimal place. That's not three significant figures, because remember, significant figures start with the first non-zero number. So when you type that in, you should get 0.255 times 0.125 will give you an answer of 0.318. So 0.31875. And so what you need to do to convert that into significant figures, it will be 0.319. Excellent, well done to everyone giving me the correct answer. So just remember, significant figures is the first three non-zero numbers. Okay. So slightly harder ones then. So now we're using balanced equations to incorporate that. So remember, we've been looking at moles before with masses. And now we're looking at the same thing with concentrations and moles, but using it, it's like a titration question, which we'll be doing next week, but it's not quite a titration question. So a student did experimental work and found that 31 centimeters cubed of potassium hydroxide solution neutralized 25 centimeters cubed of dilute nitric acid. The concentration of the dilute nitric acid was 2 moles per decimeter cubed. Calculate the concentration of the potassium hydroxide solution. So just like when we were calculating the masses using the equations and moles, it's exactly the same here, but we're using concentration and moles instead. So we start off then with all the information that we have for potassium hydroxide. So we know that we have a volume of potassium hydroxide, and we have, we have a volume of nitric acid, and we have a concentration of nitric acid. So a concentration of nitric acid is 2 and a volume of 25. So to calculate the number of moles of nitric acid, it will then be the concentration, which is 2, times the number of moles, the volume. So the volume here is 25. So 25 divided by 1,000 is 0.025. So the number of moles of nitric acid is 2 times 0.025. So what's 2 times 0.025? That's the number of moles of nitric acid. 2 times 0.025. Should give you an answer of 0.05. Great, well done to everyone answering that. So 0.05 is the number of moles of nitric acid. So if we have 0.05 moles of nitric acid, we can then use our equation, our balanced equation, to calculate the number of moles of potassium hydroxide. The ratio of nitric acid to potassium hydroxide is 1:1. So that means there are 0.05 moles of potassium hydroxide. So if we want to calculate the concentration of potassium hydroxide, we know the reaction or the equation is concentration equals number of moles, which we've said is 0.05, divided by the volume, which is 31. Again, we need to convert it to decimeters cubed, so it will be 0.031, so 31 divided by 1,000. And if you put that in, you should get an answer of 1.61 to 3 significant figures. So it's 1.61 moles per decimeter cubed. Great, excellent people that answered those questions. Okay, before we do another question, does anyone have any Q&A questions? Any Q&A questions before we move on?
I'm not sure if this one was answered, but how many marks would a concentration question be? And they've asked specifically for AQA.
Okay, so a question like the one we're doing right now would be 4 marks. A question like the ones we were doing on the page before, so this type of question here would only be worth 3 marks. And the questions that we were doing on this page would be worth 2 marks. Sometimes 3, depending on if they give you the answer and if they give you centimetres cubed or decimeters cubed.
Great, I can't see any other questions that haven't been answered, but if I've missed any, just pop them in the chat again, and then we can go through some more at the end.
Okay, so while we're waiting for more questions then, let's do the second question on this page. So a student did experimental work and found that 34 centimetres cubed of sulfuric acid neutralised 28 centimetres cubed of sodium hydroxide. And if anyone's wondering what a neutralisation reaction is, it's an acid reacting with an alkali. So sulfuric acid is an acid, sodium hydroxide is an alkali. So remember, at certain volumes, they will neutralise each other, and that's the whole basis of a titration reaction, which again, we'll be looking at on Monday. So the concentration of the sodium hydroxide was 3 moles per decimetre cubed. We've got a balanced equation there. Calculate the concentration of the sulfuric acid in moles per decimetre cubed. So again, we look at what we've got the most information for, and we've got that for sodium hydroxide. We've got a concentration and we've got a volume. So if we convert, first of all, the volume into decimeters cubed, we divide by 1,000, which gives us 0.028. And then remember that if we want to calculate the moles of sodium hydroxide, that is equal to the concentration times the volume. So we've got a volume here, we're going to multiply that by the concentration, which is 3. So the number of moles of sodium hydroxide is 0.028 times 3, which gives us an answer of 0.084. Now, if we have a look at our balanced equation, what we can see with regards to the ratio is that 2 sodium hydroxides react with 1 sulfuric acid. So if the number of moles of sodium hydroxide is 0.084, that means the number of moles of sulfuric acid is 0.084 divided by 2. So if we divide that by 2, we get an answer of 0.042. So the number of moles of sulfuric acid is 0.042. And then to calculate the concentration of the sulfuric acid, remember that is moles, which is 0.042, divided by the volume. Again, the volume is 34, but it's in centimetres cubed, so we divide by 1,000, which is 0.034. So 0.042 divided by 0.034, which gives us an answer of 1.24. So it's 1.24, so 3 significant figures, moles per decimetre cubed. Okay. Before we move on, any questions about any of these 2 questions? Someone's asking, what exam boards do most schools use for chemistry? It's AQA. Is the content the same for edXL? Yes. So everything we've covered today is also edXL and AQA questions. We'll be building on these particular concentration questions next week when we do look at titration questions, which again is in all the exam boards. Someone's asking the definition of soluble and solvent. So soluble means that something can dissolve in a particular solvent, and a solvent is what it dissolves in. Is this in the OCR exam board? So concentration reactions are in the OCR exam board. You might not see these particular questions, but concentration as a whole is in the OCR exam board. You still need to know about the different types of equations. These particular exam questions are AQA exam questions, but again, concentration is in all the exam boards. Okay. Any more Q&A questions? Otherwise, we'll do some more exam questions. Someone's asking, in page 18, is the equation for question 4 0.25 times 1.5? Yes, it is. Someone's asking, higher or foundation? These are higher questions. But you still need to know, so that this equation, molarity, is a higher tier. The foundation tier is using mass divided by volume for concentration. Good. I don't think there's any more Q&A questions. So we'll move on to some more exam questions then. So if we go back to atom economy, which is what we did right at the beginning then, so let's calculate the atom economy for making hydrogen from methane. So they've told us we want to make hydrogen. They've not mentioned carbon monoxide, so hydrogen is the desired product. So remember, the atom economy is all about MRs and ARs. So the hydrogen, there's 3 of them, first of all. So it's 6 is the MR or the AR of hydrogen. Someone's asking what level or grade would the questions be, or equation questions. So quantitative chemistry, the mathsy side of chemistry, tends to range from about a level 6 to level 7. So 6 is what goes on top for this equation. That's the AR of our desired product. And then remember, we divide that by the AR of the desired reactants or the reactants. So methane will be 12 plus 4, which is 16. And water will be 2 plus 16, which is 18. So it is 6 divided by 16 plus 18. So if you do that into your calculator, and then remember to times by 100, because we're calculating a percentage, you will get an answer of 17.64%. Does everyone agree with that? Yep, good, 17.64. Okay, great. So remember to convert to 3 significant figures, it'd be 17.6. Excellent. Okay, how about the next question then? What do we think? How would we calculate the next question? What do we need to do? They've told us we're making ethanol. Do we need to do any calculations? What do we remember about when I was talking about the Haber process? It's almost a trick question. 100, excellent. So this atom economy is 100%. And the reason for that is that all the reactants have formed one product. So there's no reason why we need to calculate the MR of the reactants and the products. Because the product is ethanol, there's one product from 2 reactants. So someone is asking, is there a way of remembering all the formulas in a rhyme or something? Because there are a lot of formulas to know. That's a really good question. So the way I remember most of the formulae, so for concentration specifically, they all kind of look the same. So it's always concentration equals something over volume. For percentage yield, again, if you think about it in the sense of percentage yield is about kind of what mass have you produced over the total theoretical mass. So if you know the definitions, you can work out what the equations are. So atom economy is about, well, how much have you produced in your product over how much is in the reactants? And then you'll remember, okay, so we look at the AR of the reactants or the MR of the reactants, and then we look at the AR of the product. And we do the product AR divided by the AR or MR of the reactants. Same with percentage yield. We know it's about the mass that you produced over the total theoretical mass. So then that means the definition of percentage yield is about how much have you produced over how much can be produced. And then again, you'll remember the definition, the reaction. So I always think of the equations in terms of their definitions rather than trying to remember all of them. But I do agree that there are reactions to remember. Good, everyone that said 100% exactly correct. Okay, what about the third one? What's the atom economy of extracting iron from its ore? How would we go about doing that? Okay, someone's giving me an answer of 70%. Do we agree? So we look at iron, that's the product. So it'd be 56 times 2, which is 112, divided by our reactants. So that'd be 3 times 12, which is 36, plus 16, which is 52 for carbon monoxide, plus our iron oxide. So remember that is 56 times 2, which is 112, plus 16 times 3, or plus 48, which gives us an answer of 160. So if we do 112 divided by 160 plus 52, we then times by 100, we get an answer of 52.8%. Yep, good, 52.8. Well done to people saying 52.8. Someone's put 70. Do you want to maybe, do you know where you might have gone wrong? Or do you know, would you need some help with that? The people that are saying 70, we've got quite a few answers coming in for 70. Do you want to tell me how you got that? Did you remember to multiply the carbon monoxide by 3? So remember, we always look at the numbers in front when we're looking at atom economy specifically. Okay, I don't think there's any more Q&A questions, so we'll do some more exam questions then. So we'll do some concentration questions. Okay, so someone's saying they forgot to multiply it, that's fine. So calculate the concentration of 3 kilograms of aluminium chloride in a 63 centimetre cube solution. So this is, these are all foundation questions. So calculate the concentration of 3 kilograms of aluminium chloride in 63 centimetres cubed of solution. What do we think? What do we need to do? What's the equation for the reaction? So someone is saying 63 divided by 3 times 100. Okay, so remember then that the grams needs to be, sorry, kilograms needs to be in grams, and this needs to be in decimeters cubed. So remember the equation is the mass divided by the volume. So the mass would be 3,000. The volume would be 0.063. So we do 3,000 divided by 0.063. Good, excellent. Mass of solute divided by volume. Well done to everyone giving me the correct equations. So the answer should be 3,000 divided by 0.063, and you're going to get quite a big answer, which is 47,619 grams per decimeter cubed. Good. Well done. Again, convert it into 3 significant figures. So 47,600. Well done to the person that gave me that answer, grams per decimeter cubed. Excellent. Okay, the next question, we want to calculate a mass. A solution of iron sulfate has a concentration of 0.05 grams per decimeter cubed and a volume of 325. What is the mass? So we're going to rearrange the equation. So mass will then be equal to concentration times volume. So our concentration is 0.05. Our volume is 325 centimeters cubed, so we need to make that into decimeters cubed, so it'll be 0.325. So 0.325 times 0.05 should give you an answer to 3 significant figures of 0.0163. So 0.0163 to 3 significant figures. And that is the mass, so it'll be grams. Excellent, well done. Someone's asking, why is the MR of iron oxide 52? It's not. I think that was on this page. 52 was carbon monoxide. 160 was iron oxide. How many significant figures do I need to round to? If they don't give you if they don't say 2 decimal places or whatever, then it's always 3 significant figures. That's the standard. Does this come in every exam board? Concentration questions are in every exam board, yes. Good, okay. So I think we'll finish there for today. Well done, everyone. There's one more concentration question on the board if you want to complete it. If not, I'll see you next week on Monday.
Great, thanks so much, Aman. And as usual, everybody, you can watch this tutorial back on my tutor YouTube channel. It'll be uploaded today. Just to flag something, there are a couple of recordings from this week that haven't gone up yet. That's just a delayed upload because of a technical issue, but they will be up there next week. So don't worry, those people asking for those. And I had a question about other types of tuition tutoring that my tutor offers. And just a reminder that if you guys want any one-to-one support, we do also have one-to-one tutoring, which you can find out about on our site and sort of have a look at what subjects are offered for that. So hopefully some of you will be joining us for our other sessions today. And we've got English, and then we've got a double maths session to catch up for the missed session on Monday. If not, then see you next week for our next chemistry tutorial. Someone's just asked, how much does the one-to-one cost? Prices vary and start at £20 an hour. might be one to chat to your parents about, and you can take a look just at mytutor.co.uk if you wanted to. Thanks so much, guys. Have a lovely afternoon, and I'll see you in another session soon. And thanks very much, Aman, for today's great session. Bye, everyone.
Bye.